Hi friends, it's Mr. Zarzak, and I am here to do an AP Newton review part 1. Will there be a part 2, a part 3? I don't know. I'm not even sure if I'm going to make it through part 1, but we're going to try. So here we go. All right, Newton's first law of motion. I'll bet you remember it. Exactly like this, every object continues in a state of rest or motion in a straight line at a constant speed unless it is compelled to change that state by forces exerted upon it. What the heck does that mean? Well, it just means that constant velocity is the norm. And if you're going to upset that constant velocity, then something external is going to come in and cause that to change. Okay, this law is called the law of inertia. You might remember from last year, inertia, resistance to change, aka mass. Is inertia mass? Well, yes and no, and yes. The more mass we have, the more inertia, the more resistance to forces. Okay, well, we need a way to talk about inertia in motion, and that's what we call momentum. Okay, so think like inertia is mass. Momentum, we abbreviate with that thing that looks like a P. It's a letter rho, or it's a P, it's a rho, it's that letter. Okay, if we slap those two things together, if we take inertia and we set it into motion, well, then we've got this thing that we call momentum, okay, which has all kinds of uses. Gives us a way to talk about the difference between like a locomotive moving down the train tracks versus like a kid on a bike. Okay, they might be moving at the same speed, but they have very different inertias, which means they're going to have very different momentums. It gives us a way to quantify these things. Okay, in terms of like units, okay, well, a standard unit of mass is the kilogram. Units for velocity is meters per second. Okay, so if I take and I slap those things together, I have the unit of momentum, which is the kilogram meter per second. Okay, no abbreviation, no fancy names with that. It's just good old kilogram meter per second. Fantastic. All right, Newton's second law. All right, that's the one that we get the equation from. That's good old F equals ma. But what does that really say? Okay, it says acceleration is directly proportional to and the same direction as the net force acting on the body and inversely proportional to the mass. Okay, so what the heck does that mean? All right, well, if I take F equals ma, all right, I'm just going to put some parentheses here to kind of make this easy. All right, let's say if we make the force bigger acting on some object, well, it's going to accelerate more. Okay, and that can be speeding up or slowing down or changing direction. All right. The inverse proportionality just says, okay, well, if we take and we increase the amount of mass, well, then for the same force, we're going to get less acceleration. Okay, so there's your inverse proportionality, and it's relative to this thing that we call the net force, which is the sum of all the forces acting on a thing. All right, so here's a setup that we saw last year. We can use to apply F equals ma. Now, again, when we write this equation, okay, we're talking about the net force, the sum of all the forces. All right, so just kind of a review of the way that we do these problems. Remember, everything's a box, okay, a free body diagram. Okay, we use that to determine all the forces that are acting on a particular object or a particular mass. Okay, so we're going to take and put the arrows on the box. All right, and then if those arrows are acting in multiple dimensions, well, then we're going to take and we're going to sum up the components. All right, and then and only then are we allowed to apply F equals ma. All right, all those forces go on one side. They got to be set equal to mass times acceleration on the other side. This acceleration, okay, that's the effect. Okay, the thing speeds up, the thing slows down, the thing changes direction. Okay, we got to have that visible acceleration. Okay, and then these forces, they've actually got to be real forces. So we have things like normal force and tension force and friction force and gravitational force. Okay, all those things that should be coming back from last year. Okay, so I'm gonna this setup here. I've got a mass. Okay, and it's on some wheels. All right, so we're gonna call this one frictionless. We'll deal with friction a little bit later on because this will keep things complicated enough. And I've got it strung with a rope over a pulley, and you can assume that a pulley is ideal. On the other side, I got another mass hanging. Okay, what's going to happen to it? I don't know. It depends on the given information. Okay, how big is one mass versus the other? But that doesn't mean we can't set it up and look at some generalities here. Okay, so everything's a box. Let's look at this one here first. Okay, well, the forces that are acting on this. Okay, so if we've got force in a rope, remember that's the tension force. Okay, and even if the mass moves down, that tension force is still going to act upwards. There's going to be some resistance, Okay, we don't compress ropes, we try to stretch them. So the tension force goes that way. All right, and then we've got the weight of this thing. Okay, remember that weight is the force of gravity, is just the product of the mass, okay, times the acceleration of gravity. Okay, and just because AP is going to do it, if they define these variables, we're going to keep them. So in this case, for this box, the weight is little m times g. All right, if I look instead at the cart over here, okay, well, that's on the ramp. All right, now there's going to be some tension pulling on the cart here. Okay, and if we don't have any information about the mass of the rope, this is idealized, well, then these two tensions, okay, for the blue box and for the red, same tensions. All right, we've got the fact that the ramp is going to support the car. We call that the normal force. Okay, and of course we have the force of gravity acting on the red car, which in this case would be like the big mass times the gravity. All right, now, as it's written, that force of gravity, or because it's at that angle that's not 90 degrees or 180 degrees or 0 degrees, okay, it's not perpendicular to the normal force, of the tension force is not very useful to us. Okay, so we've seen this trick before. All right, we can take that weight vector for the red mass there and break it up into components that are along the direction of the ramp and perpendicular to it. So in other words, we're just playing around here, okay, with shifting our coordinate axes. So we'll call this like X and we'll call this Y. Now, just so you can see it one last time, I made a little diagram down here, okay, just to make this a little bit easier to see what's going on. If this is the angle of the incline, okay, you might remember that this little angle in here, okay, is the same angle as the angle of the incline. Okay, so why the heck is that? Okay, I'm going to show you this one more time. Okay, oops, I think it's easier if I take and I just shift these arrows down to the bottom of the box here just for a second. Okay, and we'll bring this back here in just a minute. Okay, so then if this is my angle theta, okay, well then this angle here, I'm just going to call that like theta prime. Okay, and so if I take and I add together these two angles, those two angles, they got to add up to 90 degrees, right? You can see that there's like here's the triangle. Okay, so the angles got to add up to 180, and well, we know this one's 90. Okay, so those other two angles got to add up to 90 degrees as well. Okay, well, this right here, that's also a right angle. Okay, which means that this little theta prime here and then this angle over here also have to add up to 90 degrees, which means that this little angle over here, that's our theta. All right, so once we establish that, okay, that's really the trick. And then from there on out, it's just a little bit of trigonometry. Okay, so the weight vector, which is just pulling down on this, and I guess if I really wanted to be picky here, I could take and shift this back up to the middle of the box. Try to get that out of there. There we go. Okay, we don't really need theta prime anymore. Okay, and let's bring this back over here. Okay, so this is like the big mass times gravity. Okay, and so this would be, we call this one FG X, who's got like our XY plane here. All right, so that would be the big mass times gravity times, it would be sine of the angle. Okay, and then this piece over here, that X perpendicular to the ramp, that'd be like our FGY. Okay, it's right next to the angle, so it'd be like big M times G times cosine of the angle. Okay, so that's where all that stuff comes from. So if I just kind of sneak back up over here, I'm just going to take and I'm going to remake my free body diagram. Okay, and just to keep it in, to put it in form that's convenient. So this would be that's our FGY. So that's our big M times little g times the cosine of the angle. Okay, and then this one here, that's our FGX. So that's big M times g times sine of the angle. Okay. All right, so let's go to the blue box first. All right, and since the blue box is pulling down on the cart, to me in my brain, it just kind of makes more sense to say, all right, well, like the motion's most likely, to me, this is the way I'm going to picture it happening, so I'm going to make that positive, and it's just a choice. Okay, if that's the case, okay, if I look at the blue box, well, then I've got the F of G minus the tension, okay, causes the blue box to accelerate. So I got my net force on the left side, and I got MA on the right side, where that M is the little m. Okay, So I'm just going to write that. I can take that to Fg minus Ft equals ma. Okay, so that's one equation that could be kind of useful to me. And I'm just setting up equations here. There's no numbers. Okay, the numbers are going to change from problem to problem. So the equations we use and how we put them together is going to change from problem to problem. If I look at the red box here, okay, so if I look at my x direction here, all right. Well, if I set down as positive over here, okay, well, I want to stay consistent with my positive direction. See, so like up the ramp is going to be my positive direction here. So I've got along this my x dimension, okay, that tension force, all right, minus the mg, that's the big M, sine theta is equal to m ax, okay, and then up and down along my what I'm calling my y dimension, I've got, let's just make this way positive as well. So I got normal force, okay, minus big mg times cosine of theta is equal to ma y. All right, now typically with these ramp problems, either we're going to drag the cart up the ramp, or the little blue hanging mass isn't going to be enough, so it's going to fall down the ramp. All right, point being is that like the motion's like along the ramp. All right, so typically, okay, that this is going to be 0. So that's typically. Okay, hesitate to say always, because as soon as we say always, then we see some problem where we're going to launch the car off the ramp like a rocket or something. Then the other thing is that, well, if the blue mass over here accelerates downwards, well, then that means the cart accelerates up the ramp. So at least in terms of the magnitude, these two accelerations, okay, those are going to be the same size accelerations. Okay, and so I've got 3 different formulas, okay, that can be useful to me, all right, depending upon what's my given information, what I'm being asked to solve. Okay, so that's just kind of the basics. You've seen these setups before. It's just been a little while, so just kind of refresh your memory. All right. And of course, well, we've been working with calculus. So guess what? Okay, so now we're going to apply calculus to Newton's second law. All right. Before we do that, some other things, okay, some other background information that we want to have. Okay, we've seen this before too, this concept of impulse. All right, so remember in physics, we tend to just kind of slap variables together and see what comes out if there's something that's useful to us. Okay, and this impulse thing, it is very useful to us. This idea of impulse, okay, impulse is equal to the change in momentum. Okay, the analog here would be like work is equal to change in energy. All right, the way that we get it, okay, this impulse is we take the product of force and time. So in terms of like units, okay, well, we know like the units of force is the Newton, and the standard unit of time, that's the second. So you slap those two things together, and the unit of impulse is the Newton second. Okay, that's Newton's time seconds, not divided by. All right, the effect of applying a force for some amount of time, okay, is that you're going to get a change in momentum. Now, typically what's going to happen here is that momentum change comes from inertia changing its state of motion. In other words, like a mass undergoes a change in velocity, okay, when an impulse is applied. All right. If I take and I look at these two things together here, and by that I mean like if I take force times time is equal to mass times this change in velocity. Okay, well, when we talk about time, like if we start our stopwatch, we're going to start our stopwatch at like 0 seconds. Okay, so really this is just some time interval. Okay, so like technically speaking, that's force times the change in time, but we typically don't write that delta because we're lazy. But I'm going to write it here too because it's going to make this a little bit more convenient for me to see what's really going on here. And look, if I take mass times the change in velocity with respect to time, okay, well, what is the change in velocity with respect to time? That's acceleration. Okay, so all this stuff is just ways to re-envision Newton's second law, okay, depending upon the information that we're given, okay, and what we're trying to solve for. Okay, this kind of setup becomes really useful when we start to apply calculus. All right, let me show you what I mean. Okay, so using that same combo, force times time is equal to mass times change in velocity. Okay, well, that delta is just any old change in velocity, right? By that same token, okay, we can apply a force for as much or as little time as we want to, right? So that t is really a delta t. Okay, so now let's look at what happens when we shrink those two changes down to infinitesimal, okay? So in other words, like if the force if we look at it and how the effect of the force changes over a small period of time, okay, that's analogous to saying, let's look at how the mass changes with a small, or look at how the momentum changes with a small change in velocity. Okay, once I see these operators, okay, right, so small change in time, small change in velocity. Okay, so now we're getting in the calculus world. All right, and now we got a bunch of options as to what we can do. All right, if I take and I divide over the dt to both sides, okay, I can isolate the force, okay, as a function of time and set that equal to mass times change in velocity over change in time. And what are we really talking about here? That's the acceleration. That's good old Newton's second law. All right. Ta-da. That's kind of cool. All right, but wait, there's more. Okay, if I have a setup like this where I see, you know, a d to something on one side and a d to the other, okay, well, that's kind of a hint to integrate, right? So like if I, if I got like dv over dt, that's derivative of, okay, if I've got just dt on one side and dv on the other, I can integrate both sides. Okay, so I have two useful approaches. Okay, so I've got this from the perspective of I'm going to differentiate, or here I'm going to integrate. Okay, and so how do I know what to do? Well, it's just a matter of what's the given information, what it is that I'm trying to find. Okay, so the way that we apply it, the way we figure it out is we do what we always do, which is we do some practice. All right, and so that's exactly what we're going to do. All right, so a crossbow can fire a 0.1 kilogram bolt at 40 meters per second. It takes 0.05 seconds for the bolt to be accelerated up to speed. Assuming the force is constant, what force does the crossbow exert on the bolt? Okay, so just going to pop through here and identify knowns and unknowns. All right, so I got 0.1 kilograms, so that's our mass. All right, the crossbow can fire it at 40 meters per second. So when the bolt leaves the crossbow, it's moving at 40 meters per second. So that's a velocity. Okay, and specifically, that's a final velocity. See, so like you load the bolt into the crossbow, and before you pull the trigger, it's just sitting there. Okay, so that initial velocity is something that we have to infer. It's just zero. Okay, if I look at the difference between those two, that's the change in velocity. All right, it says here it takes about 0.05 seconds for the bolt to be accelerated up to speed. So I've got a time frame of 0.05 seconds. Okay, and remember, that's really just the delta. That's the change in the time. That's how long it takes for it to fire this thing. Okay, so it says assuming the force is constant, what force does the crossbow exert on the bolts? Okay, so Newton's second law says F equals ma. All right, well, remember that the acceleration is really just the change in velocity with respect to time. Okay, so if I have a 0.1 kilogram mass, all right, the change in velocity, so 40 minus 0 is still just 40. So I've got this, 40 meters per second. Okay, and it takes 0.05 seconds to do that. All right, so math, and don't tell anybody, but I have a little cheat sheet over here so that I don't have to do the math. Okay, so I get 80. Okay, now this is newtons. All right, if we look at the units, just so we can see it, if I took, so I'm taking kilograms times meters divided by seconds again, there's kilogram meters per second squared. That's mass times acceleration, that's newtons. Okay, so there's your basic, okay, F equals ma kind of problem without calculus. What about one that requires calculus? Here's one. Okay, it says, of course, the crossbow does not apply a constant force on the bolt. Assume the force is a function of time where F is equal to 90 minus 9,000 t squared. All right, this crossbow fires at 0.1 kilograms. It takes about 0.1 seconds for the bolt to be accelerated up to speed. What's the final speed of the bolt? Okay, so similar kind of problem, but just with a different request. Just to figure out what is VF. All right, so again, all of this just comes from force is equal to mass times acceleration. Now I've got this function, okay, that describes the force. So that's kind of a tip-off that maybe some calculus is going to be involved. All right, so I'm going to take F equals ma, okay, and I'm going to write it as the change in velocity with respect to the change in time. Okay, that infinitesimal. Like, this is really the generalized form of Newton's second law. Excuse me. All right, now I have a function for force. Okay, and it says, what's the final speed of the volt? So I'm interested in finding velocity. Okay, well, right now as it's written, it's like dv is in my equation. I don't want dv. I want something that's going to say velocity so that I can get an answer. Okay, so that's kind of the tip-off. All right, so what I'm going to do here, work a little bit of magic. Give myself, that didn't work. Let's try that again. Let's give myself a little space. That's what I'm looking to do. All right, and let's move that dt over there. Okay, and this force varies with time, so I'm going to write that as f of t, just as a reminder to myself that, hey, force is a function of time. dt is equal to mass dv. All right, so I've got those little d operators on each side, which says, all right, time to integrate. All right, it says the crossbow fires the 0.1 kilogram bolt. It takes about 0.1 seconds. So in terms of my force, okay, that means definite integral. So from time 0 to time 0.1 seconds is the interval over which I'm going to integrate the force function. Okay, and well, for the mass dv, okay, well, the variable is velocity. The mass is just some constant, okay? And so I'm going to integrate over the initial velocity to the final velocity. That's my interval, all right? So 0 to 0.1, okay, my force function is 90 minus 9,000 t squared dt is equal to, all right, now watch this. I'm going to take, since that mass is just a constant, I'm going to pull that out in front of that summation, the little integral sign. You can do that with constants. All right, so really I'm just integrating dv, okay, over this course of vi to vf. Okay, so now I'm going to go take the integral on the left side, so I have 90t, okay, minus 9,000 t cubed over 3, and again, I always do that because if I don't do that, I screw it up. Okay, and I'm going to evaluate the integral from 0 to 0.1 seconds. Okay, and that's going to get me, okay, the integral of dv is just, well, v. Okay, and I'm going to evaluate that over vi to vf. All right. So a little simplification. So let's see. So 9,000 over this would be 3,000 t to the third power from 0 to 0.1 is equal to mv from vi to vf. Okay, so some good news here is that when we fire the crossbow, the bolt is initially at rest. Okay, so if I evaluate over here, so I got 90.1, okay, minus 3,000. 0.1 cubed. Okay, 90 times 0 is 0. 3,000 times 0 cubed is still just 0. Okay, so there's nothing going on at 0. So that's kind of nice. All right, and over here, mass times velocity. If my initial velocity is 0, well, then this just becomes VF. All right, so let's see. So 90 times 0.1, that's 9. Okay, 0.1 squared would be 0.01. So 0.1 cubed is 0.001. So 3,000 times 0.001 is 3. Oh, that's convenient. Okay, is equal to mass times the velocity final. Now, just so you can see it, okay, what this really is, all right, is this would be like Newton seconds, and this would be Newton seconds too. So we're looking at these impulses, okay, or if you prefer, well, like this is a time value, right? So like the 0.1 is a second, okay, well, mass times velocity, or mass times change in velocity, that's your impulse, which is that's got to be newtons times seconds, okay? Anyways, so if I subtract the 2, 9 minus 3, it's just 6 Newton seconds. Okay, and that's equal to mass times the final velocity. And what the heck was the mass of this thing? It was 0.1 kilograms. Fantastic. Okay, so if I take 6 newtons times seconds, 0.1 kilograms times VF, so then it's take and divide out the mass. Okay, and that's going to give me my final velocity. So 6 over 0.1 is 60. Okay, and if you really want to torture yourself, well, remember, Newton is the kilogram meter per second squared. So I take that and multiply by seconds and divide by kilograms. Okay, so let's see. So kilograms would factor in one of these and look, meters per second. All right, which is pretty disgusting. So get rid of all that noise. 60 meters per second. All right. Ta-da. All right, right, let's do another one. So an unusual spring applies a varying force when compressed. Okay, so this is not a Hooke's law spring. Experiments determined that the velocity object with the mass of 2 kilograms has the following function. Okay, so I got a velocity function. It says write the equation for force at any time. All right, well, we know F equals ma. Okay, we're given the mass, that's 2 kilograms. All right, so really it's just a matter of figuring out what's the function that describes the acceleration. Okay, and well, we know that the acceleration is just the derivative of the velocity with respect to time. Okay, and since I have the velocity function, all I got to do is take the derivative. Okay, so 4t squared, so that would be, what would it be, 8t. Okay, plus, let's see, so 2t, so just be 2, and that minus 4 is 0. Okay, so there we go. So I got 8t plus 2. All right, and so because F equals ma, or if you prefer, more generalized, m dv dt, so I'm just going to take the mass, which is 2 kilograms, all right, and multiply that by the function for the acceleration. So I'm left with, let's see, so this is 16t plus 4. All right. Just for good measure, okay, if I wanted to put units with the coefficients just so you can see it, okay, well, the answer is force is equal to this thing, right? Okay, so that just means that, so what would it be? That would be 16, so that'd be, I need newtons, so I'm going to do newtons divided by seconds so that when I multiply by time, okay, the time would be in seconds, so the seconds would cancel out, so it'd be 16 newtons over seconds plus 4 newtons, okay, and that would be the function with proper units. Okay, so I guess, like, technically speaking, that's the real answer. Okay. All right, here we go. A 100-kilogram box is pushed by a very energetic worker moving the box with a force equal to 3t squared. Okay, so force is a function of time. All right, that's a good clue that we're probably going to need to either integrate or differentiate. If the box is moving at 3 meters per second at 2 seconds, how fast is it moving at 4 seconds? All right, so F equals ma. Acceleration is the derivative of the velocity with respect to time. Okay, so I've got some force function here. Okay, and I've got information that says the box is moving at 3 meters per second at 2 seconds. So I'm being told here, look, like, here's a velocity at a certain time. So what I really need, I need a function for the velocity. Okay, so that's kind of like what tells me what I need to do. Okay, the force is a function of time. So I'm going to take and move that over. Okay, that's kind of the tip-off, is I got to get that velocity function, which means we're going to integrate. All right, now we have a specific value for the velocity at a specific time. That's not an interval. Okay, so these are indefinite integrals. All right. So let's see. So I have 3t squared dt is equal to mass times integral of dv. All right, so let's see. So I got, that would be t to the third power plus c, okay, is equal to mass times some velocity plus a c. So now technically speaking, we've got two constants. Okay, so we're just going to take them and combine them together. All right, I'll do it on the left side. Okay, and there we go. Okay, so there's my expression for velocity. Okay, and so now, once I have that, well, I got 3 meters per second at 2 seconds. Okay, so I'm going to take and I'm going to evaluate my function at this specific time. So when time is equal to 2 seconds, so I'm going to take 2 to the third power plus my constant. All right, and I'm told the mass is 100 kilograms up in the top there, so there's my m. Okay, so when time is 2 seconds, I'm moving at 3 meters per second. So I'm just subbing in values so that I can solve for that constant. Let's see, so 2 to the third power, let's see, 2 squared is 4, times 2 is 8. So I have 8 plus c is equal to 300. All right, and then I'm just going to subtract over the 8. Okay, and so I get c is equal to 292. Okay, so once I got the constant, well, then I can take and I can write the generalized form of the equation. All right, so plus 292 is equal to 100 for the mass times the velocity. Okay, or I guess if I really want to make this in terms of the velocity, I could write it this way. So V is equal to T cubed plus 292 over 100. All right, once I got that expression, okay, so this is how fast is it moving at 4 seconds? Okay, so we're going to solve for the velocity when time is equal to 4. No problem. All right, so 4 to the third power plus 292 over 100. So let's see, so 4 squared would be 16 times 4 would be 64 plus 292 over 100. So whatever that is, and I don't have the brain power, so I'm just going to cheat. Don't tell anybody. I get 3.56, which sounds about right. That'd be 300 something over 100. Yep. Okay, so 3.56 meters per second. All right. And that, ladies and gentlemen, is enough for part 1 of this here screencast. So we're going to pause it right there. All right. Feel free to go back and review these things. All right. And I'll see you around. Have a good one. Mr. Zarzik saying bye-bye.